interest, but we only have adequate training data in another domain of interest, where the ladder of data may be in a different feature space or follow a different data distribution. In such cases, knowledge transfer, if done successfully, will make an improvement for the performance of learning by reducing the cost for data labeling efforts. So in recent years, transfer learning has emerged as a new learning framework to address this quandary. These special topics focus on the current progress on transfer learning for classification problems. In this project, we discuss the relationship between transfer learning and other related machine learning techniques such as multi-task learning. We also explore some potential future issues in transfer learning research. And from this picture, we can see that AI, which is a very large research field, means any technique that enables computer to mimic human intelligence using logic, if-then rules, decision trees, and machine learning. And machine learning is a subset of AI, and deep learning is a subset of machine learning composed of algorithms that permit software to learn itself to perform tasks like speech and image recognition by exposing multi-layered neural network to vast amounts of data. And from this timeline, we can see that AI, which comes first and also the largest, and then is the machine learning, which goes later, and finally is the deep learning, which driving today's AI explosion, which really inside both of them.
Alright, so let's move on next slide. So 1.2, convolutional neural networks. There are several layers here. So first step is input. There's a feature. So and also example. So for example, that it might be image, it might be for some big data there, and then it goes into convolutional layer. Okay. So there's 1, 2, 3, 4, 5, 6, 7 layers there. Okay. So but there's still big size there, right? So we try to use the size there. So pulling important role in reducing the size, right? So you can easily tell that. So who makes how to make a small size, right? Okay. So we got a little small size. That's very important because we can reduce the time when you compute the data, right? So and repeating, you got here fully connected. So these steps, the process of fully connected, so making the output. So you put it into here. There's the p given x, and you get the output, which is y hat, right? It might be a logistic model, so you can get 0 and 1, like a cat or not cat, or you can, if you use software machine, you're gonna get the multiple output. Okay. Sorry. Alright, 1.3 software and hardware requirements. Alright, so these are the list of software we use. Okay, first one TensorFlow and Keras, and then Matplotlib, and so on NumPy. Okay, there's something we use for this project, and then hardware. I did the research, so in order to get the compute all the data, big data, so we need this amount of hardware. Okay, strongly recommended. It's not necessary, but if you have it, that's really good. Okay, you can compute very fastly. Data that we use, okay, ImageNet with the data over 50 million labeled high resolution image belonging to roughly 22,000 categories. Okay. The ImageNet large-scale visual recognition challenge is a benchmark in object category classification and detection for hundreds of object categories in linear image. Okay. ImageNet challenge uses a subset of ImageNet with roughly 1,000 image of 1,000 categories. In in all, there are roughly 1.2 million training images, 50,000 validation image, and 150,000 testing image. It's a lot though. Okay, so the only version of ImageNet challenge for which this test data were available. So we're using that data because it's really large though. So this is the version on which we perform most of our experiment. Okay, so CNN, so convolutional network architecture. So mostly use AlexNet, VGG that we use. Okay, Google Net and AlexNet. Okay, so AlexNet is very popular because AlexNet was first place ImageNet challenge 2012. Okay, test error, top 5 test error of 16.4%. It was really good. After 2 years, the VGG got 7.3% top 5 error. So which is they got improved anyway. But this is not the first place. The first place is Google Net. Okay. As far as I remember, it was 6.8%. It's not quite different. Okay, it's slightly similar, but a little bit better Google Net. Okay, Google Net did a little bit better. Okay, AlexNet is a famous, like, AlexNet did an excellent job when they classified letter. But BGG, so it did a good job when you classify image. Okay, they're totally different character and totally different role. Okay, Alex is like when you classify letter or number, and BGG classify image. But we're gonna do the image, so you definitely gonna use BGG, right? Okay. So also there are a lot of architecture. So mostly recently comes. Okay. So I really want to explain this, but I didn't study much. Okay, we can skip that. Okay. The BGG architecture. So BGG architecture, network architecture was introduced by these guys. Okay, in their 2014 paper. Okay, so I don't want to pronounce it wrong. Okay. A very deep convolutional network for large scale image recognition. I told you. So this kind of famous when you classify image, right? This network is characterized by its simplicity, using only 3x3 convolutional layers, stacked on top of each other, increasing depth. Okay, that's a kind of keyword. Okay, 3x3 convolutional layers. Okay. And next one, reducing volume size is handled by maximum pool. So when you think about BGG architecture, that's a keyword. First one, 3x3 convolutional layers, okay, and max pooling, okay. There's two different things. And then Google Net and BGG, they're very similar. But BGG using 3x3 convolutional layers only and max pooling. Now you can tell the difference. Okay, so I just want to go over how to compute. Okay, so somebody created descent. First of all, when you have several layers, right? And let's say we have 3 layers. So first layer, second layer, third layer is output. Okay, so first thing we have to do forward propagation, and then do the backward propagation and get the parameters, right? Okay, so this is vectorization. Okay, so I think the most important part when you compute gradient descent, you have to match with the dimension. Okay, so because when you do the compute, so you might make mistake a lot in that part. Okay, so this is kind of important, I think. So keep dimension true. So which means that they try to make 2 dimensions from the 1 dimension. Okay, and also these are all the gradients from derivative. Okay. All right. Next.
So here I'm going to explain some difference between transfer learning and multitask learning. So multitask learning is a technique that it's used to contain multiple related tasks and help to improve the generalization method of all the tasks. On the other hand, transfer learning is a machine learning technique where a model is used as a starting point for a second model to do as a pre-trained model for the second. And so in multiple task learning, one image can have multiple labels, and like in softmax regression where one image has only one label. So basically in transfer learning, we retrain all the layers if we have more data, and then we retrain the last layer only if we have a small data. In our case, which we have only 2 pictures that we use to the weight from the VGG16 to train our model. So we use a recently developed regularization method called dropout, which proved to be very effective. As we retrain the VGG16 data, by training the architecture, it's hard to find the optimal hyperparameter for each architecture. So in large neural network require a lot of computation, even if one was able to do in a network using them all, it's going to be a hard task to do and feasible at the test time. So by using the drop-off, it's help us prevent the overfitting and provide a way of approximately combining and exponentially many different architectures. So by dropping out a unit, we mean temporarily removing it from the network along with all its incoming and outgoing connection. Each unit is written with a fixed probability P, independent of other units. So it's like when we have the network, so when we apply the dropout, so this neuron can no longer rely on any one previous neuron features, because any one feature can be just by setting the probability, usually they set at 0.5, it can be removed. So we have to spread out the weight. And at test time, we don't use dropout because it's just gonna add noises to the prediction.
Details of learning. So we try to train the large, deep convolutional neural network to classify the 1.2 million high resolution image in the ImageNet data. So context. Our initial neural network has 60 million parameters and 650 neurons and consists of 5 convolutional layers. Some which are followed by max pooling layers. I told you that's the BGG. And 3 fully connected layers and with final 1,000 ways of the max. Unfortunately, it takes several weeks and a very expensive, efficient CPU implementation of convolutional operation. So we decided to download the weights and use them as pre-trained for our topic. Okay. All right. This is a kind of graph. Smaller network converge and were then used as initialization for the large and deeper network. This process is called pre-train. Okay. All right. Next one. Result.
So as you can see here from the results, when we use the VGG16, this image is coming from the ImageNet, and the accuracy was 93%, which is pretty good for the classification. And then when we just use one of our image, here it looks like the classifier. Yes, it's the giraffe. So we use, so because that image wasn't part of the image in the VGG16 model, so it was classifying as Chia or something with 0.73. And then we use a picture. I just upload and see the prediction wasn't good, as it says seabed is given some probability noising or so. So we train only, so what we did is we take our 2 images and we we process them by creating using using okay, so this is what we use. We installed this package Augmentor from Jupyter Notebook, and we just initialize our two images, and we use some probability like rotation, flip blur, and bottom cropping, random resizing to create a 100 sample size.